Okay, this is the second half of 14.5, curvature and normal vectors. We're coming up to an example problem that's pretty long, so I've pasted it out onto its own, I've cut it out into its own page here. Let's jump in and see what it does. So we just got a formula for the unit normal vector, the principal unit normal vector, that is actually usable when we have a parameterization in terms of time. So let's see how to use it. So first it says, this question says, find n of 4 for the above vector valued function. Just to remember what we're talking about, this is the vector valued function that we were dealing with earlier that followed the curve y equals minus square root of x. And at time t equals 4, we were at the point 4 minus 2. And we knew that the unit tangent vector, which we got a few pages ago, I want to say, the unit tangent vector, went mostly to the right and a little bit down. And remember, this is a unit tangent vector, so it goes in the direction of the curve, but it has magnitude 1. Now we're trying to find the unit normal vector. Based on the way that what we were trying to do when we created the definition of the normal vector, we want to say well, the principal unit normal vector should tell us which way the curve is curving. So I'm hoping that our formula gives us a vector in this direction. Because the unit tangent vectors are going southeast, but they're flattening out. If you were driving on this path, you're kind of turning left. You're turning into the curve. And so I'm hoping that we get a unit normal vector that goes this way. Knowing what the unit normal vector is supposed to do helps you check your work. So it's important that you have an idea for what you're aiming at before you actually do it. So let's find n of 4. To find n of 4, we're going to have to, we have this formula up at the top. So we need t prime of 4 divided by the magnitude of t prime of 4. Okay, well, how do I find t prime of 4? I can't take the derivative of t of 4. That's not how that works. Instead, I have to go back and get t of t, which we had, oh my gosh, what was it? I think it was 2 root t over square root of 4t plus 1 and minus 1 over square root of 4t plus 1. So we calculated this before. So to figure out t prime of 4, I'll have to first find t prime of t. So let's go get that. So I'm going to try to get t prime of t. And here is a theme that's kind of repeated throughout calculus, but gets more and more important as you go through it, which is the theme that you need to be lazy in a productive way. When you look at this and you say, aha, the formula is telling me to take the derivative of this function, you should think, no, I don't want to. Because realizing that you don't want to do the quotient rule makes you think, oh, maybe there's a way out of it. And in this case, there is. I'm going to factor out the scalar square root of 4t plus 1 from both components. So I'll end up with 4t plus 1 to the minus 1/2, factored out of the vector. I didn't actually take the derivative yet. But by factoring this scalar out, it allows me to take the derivative using the product rule, and I won't ever have to take the derivative of anything too complicated. So let's get t prime. I'll use the product rule here. I'll do the first times the derivative of the second. The derivative of square root of t is 1 over 2 square root of t. So here I'll end up with 1 over square root of t. And the derivative of minus 1 is 0. So here's the first times the derivative of the second. Then I'll do the derivative of the first. Make sure to get the chain rule in there and leave the second alone. So this problem is very long. We're not close to done with it. And the thing I'm most worried about is that you'll look at this problem and think, oh, I'll never be able to do that. But that's not the case. these tactics of like taking a problem that's painful and splitting it up into little pieces so that the individual pieces are easy, that's kind of like the core skill here. So you see something you don't want to take the derivative of, well, do some algebra to make it more reasonable, and then you can do it a little bit at a time. Okay, now we come up to a second tactic that's important, which is, do I need to simplify this? I'm worried that in algebra and maybe even earlier calculus classes, you may have been trained that you should always simplify everything. That's not the case. You should simplify things when it's useful to simplify things. Here, are we going to need to do anything with this other than plug a number in? If we're going to need to do anything with this other than plug a number in, then we should simplify it. But no, all I need to do with this object is plug 4 in for t. So I don't try to simplify it, I just plug in 4. So that's what I was looking for. So you can't be on autopilot while you're doing these problems. You need to like make the problem easier when it's hard, and then don't do busy work unless you need to. So plug in 4, I get 17 to the minus 1/2, 1 over square root of 4, minus 1/2. Okay, here I get 17 to the minus 3/2. The negative exponent puts it in the denominator. The 3/2 power means you need an entire 17 and a 17 to the 1/2. In a way, you can think of 17 times the square root of 17 as 1.5 copies of 17. That's what the 3/2 power does. I'll just keep plugging in 4 here. What does all this do? This is like kind of a huge mess. Do I need to simplify this? So I'm again asking the question, like, am I going to need to do anything with this vector? If so, I need to simplify it. This time the answer is yes, I'm going to need to find the magnitude of this vector, so it is actually worth my time to try to write this in some reasonable way. But I saved a lot of time by asking myself that question earlier, like, do I need to simplify this? The answer was no. And now, do I need to simplify this? The answer is yes. So I'll factor out this 1 over the square root of 17. I'll end up with 1/2 0. 4 divided by 2 is 2. So I guess I'm going to have minus 2/17 times 4 minus 1. Is there anything else I can factor out? Not really. If you know that at the end of a calculation you're going to take the magnitude of a vector, factoring out scalars from it is super powerful, because the magnitude of a scaled vector, you just get to keep the scalar on the outside. Okay, so negative 2/17 times 4 is negative 8/17. And negative 2/17 times minus 1 is plus 2/17. Now let's get these combined. In the j component, I'm just going to have 2/17. Because I have 0 plus 2/17. In the I component, in the x coordinate, I'll have 1/2 minus 8/17. Minus 8/17 is almost 1/2. Like 8/17 is almost 1/2. So I'm expecting a really small number here. 1/2 minus 8/17 is 17/34 minus 16/34. So I get 1/34. It looks like I can factor out even more stuff, so I'll factor out a factor of 17. I'll end up with 1/2, comma 2. So this is my t prime of 4. Yeah, okay, so what were we trying to find? We're trying to find n of 4. We found t prime of 4. Now I need the magnitude of t prime of 4. So I'll take the magnitude of this thing. If you have a scalar and you're taking the magnitude, you get to keep the scalar. And then find the magnitude of this vector. throughout dealing with this problem, we have had so many, this is how the 17s get generated. So if this is 4 and a fourth, that's 17 fourths. So I end up with root 17 over 2. And these cancel, so I have 1 over... I'm not sure if it's worth it to combine the 17 and the 2. I think not. You'll see why in a minute. What you should be taking away from this is, first of all, like how the formulas work, but second of all, like these tactics to make the problem easier. The tactics are mostly not doing work until you're sure it's necessary. Here I didn't even multiply 17 times 2 because this is a scalar I'm going to be dividing by, and multiplying it out probably will just cause me to have to break it up again. So I'm leaving it this way. So anyway, if we can finally get n of 4, this is the principal unit normal vector. It's t prime of 4 divided by its magnitude to make it a unit vector. So I have my t prime of 4 from before. And then I need to divide by this fraction. Dividing by this fraction is multiplying by its reciprocal. Looks like the 17s cancel. And when I combine this all together, in the x-coordinate, the 2 and the 1/2 will cancel, so I get 1 over root 17. And in the y-coordinate, I get 2 times 2 over root 17. Okay, we did it, but we also knew what the answer was supposed to look like. The answer was supposed to look like it was going northeast, and a lot more north than east. Like it's supposed to be like to the right and up, but more up than to the right. So we can check our answer, and yeah, that looks like about what we were expecting. So n of 4 is a normal vector, and it points in the direction that the curve is curving. So that's n of 4. This question has a bunch of other things to ask. Some of them are very easy. One of them is find the magnitude of the unit tangent vector. If someone asks you to find the magnitude of the unit anything, you don't have to do any calculations. It's 1. That's the whole point, is that it's a unit vector. It has magnitude 1. So the magnitude of t of 4 is 1. Why am I wearing these? I really don't need to be wearing these. Then it asks you to find the magnitude of n of 4. Again, this is a unit vector, so if we did this correctly, the magnitude is 1. That just always happens. That's why it's the unit normal vector. Here, if you check this, if you square both of these, you'll get square root of 17 over square root of 17 when you add them together, so it does work. Finally, there's one more thing we're supposed to look at here, which is n of 4 dotted with t of 4. Remember back in chapter 13, and what is the point of a dot product? The main point of a dot product is to check whether two things are perpendicular or orthogonal. Here, looking at my picture, you can see that the way I drew it, they look like they are orthogonal. So you should expect t of 4 and n of 4 to be orthogonal. You check that by finding their dot product. So let's just do it. T of 4 was 4 over root 17 minus 1 over root 17. And n of 4 is this thing. When I dot them together, I get from the x-coordinate 4/17, and from the j component, or the y-coordinate, I get minus 4/17, so I get 0. That means that the unit tangent vector was perpendicular to the principal unit normal vector. The fact is that that always happens. So when we go on to the next page, we'll see why that happens. So the unit tangent vector and the unit normal vector, they're always perpendicular. Why? Okay, well, let's look at it. So to see if things are perpendicular, you should dot them. If you're stuck in the middle of a proof, you should look at the most complicated object and break it up into its definition. So the unit normal vector, we like, we have a formula for finding it. It's t prime of t divided by the magnitude of t prime of t. Okay, here I've got some vectors dotted and a scalar. The point of this proof is to show that two things are perpendicular, so I'm not really interested in the scalar. I'm hoping that I can show that these two, that the dot product of these two vectors is 0. So if I don't want to think about this anymore, and you can always do this anytime you're like considering a new object and you're not looking at the whole thing that you were working on before, we can say consider to like change the subject. So let's consider t of t dotted with t prime of t. Okay, if we look at that, t dotted with t prime, this is going to look very weird, but it's a thing that you can do. You could say that it's half of itself added to itself. Let me write it down first. So here's t dot t prime. The order doesn't matter for the dot product. And here's t dot t prime. If I have two copies of t dot t prime, that's twice as big. So t dot t prime is definitely half of two copies of t dot t prime. Why would anyone ever do this? The reason is because this second version looks like the product rule. So that means what's really going on here is that this is half of the derivative of t dot t. If this is easier to see going in the other direction. If you took the derivative of t dot t and you did the product rule, you do the first times the derivative of the second and the derivative of the first times the second, you'd get this thing up above. Now, okay, I guess, like what are we doing? Well, what we're doing is that if you dot a vector with itself, that's the path to finding its magnitude. So this is half times the derivative of, this is the magnitude squared. But what is the magnitude of t? Remember, capital T is called the unit tangent vector, so its magnitude is 1. So this is half times the derivative of 1. Well, the derivative of 1 is 0. So what did we actually show here? What we showed is that if you take a unit tangent the unit tangent vector and dot it with the derivative of the unit tangent vector, you can do like some, I don't know, this is like a parlor trick, really. If you take more abstract algebra or analysis classes in the future, like these would be 400 level type classes in the math department at a transfer institution, then you'll learn there's some bags of tricks like this. But this is, you should imagine I like did a trick to do this. You should believe that they're equal. What should probably still be mysterious to you is like how I would know to do this. But basically t dot t prime we showed is actually 0. So that means that t dot n, which has this 0 as part of it, here's 0, is also 0. So t dot n is 0. What does it mean if you dot two vectors and you get 0? That means that they're perpendicular. So the unit tangent vector and the unit normal vector, in our example, they were orthogonal, but this proof shows that that actually always happens. And the reason is because the unit tangent vector is a unit vector. So this is guaranteed to happen. Okay, what's up next? Okay, what's up next is that the last objective, the last two objectives up above me, are to figure out what the unit tangent vector and the unit normal vector have to do with acceleration. And our kind of ultimate goal at the end was to figure out how to show, like how to calculate whether a curve is just curved in a plane or if it has torsion where it's twisting like a helix. The way to get to that is to talk about how the acceleration vector has two components. You can break the acceleration vector up into some of it is in the n direction and some of it is in the t direction. So this is kind of weird. If you have a curve that you're following and you're at a point, you get a unit tangent vector that tells you your direction, and you get a unit normal vector that tells you which way you're turning. This is n, and this is t. The acceleration vector is kind of like a whole different thing. Depending on what's going on as you're going along the curve, the acceleration vector might be completely just the amount that you're turning. Or it might be that you're like speeding up as you're driving. If you were accelerating while you were turning, your acceleration vector might be off in this direction. The point of this theorem is that the acceleration vector can be almost anything, but the acceleration vector doesn't escape this plane. So the acceleration vector does not come out of the page at us. In fact, it's kind of like locked into the two-dimensional plane defined by the unit tangent vector and the principal unit normal vector. In this case, the way that we'll show the acceleration vector is a combination of the unit normal vector and the unit tangent vector, is to explicitly show how much of each are included in the acceleration vector. So this is our plan. Our plan is to just write the acceleration vector, as a combination. So we're going to have like a t part and an n part. We'll think of there being two pieces of acceleration. The acceleration that comes from the tangential component. So this is like how much you're speeding up or slowing down on the road. This would be if your speedometer is going up, you'd have positive a sub t. This is the part that tells you whether you're speeding up or slowing down on the road. And then a sub n is the part that tells you how much you're turning. So this would not be visible on your speedometer. We'll have to find what a sub t and a sub n are, but we'll be able to do it. So here's how. We start by just writing down the definition of what the unit tangent vector is. The unit tangent vector was, we took the velocity vector and we divided it by its magnitude. Remember, the velocity vector is a tangent vector, but this is the unit tangent vector. So we'll need to divide by its magnitude to get the unit tangent vector. Let's rearrange this. Remember, between two equations that are true, you can put an arrow. So when we rearrange this, we will have that the velocity vector comes from the speed times the unit tangent vector. Okay, the reason I did this is because now I can take the derivative with respect to time, and on the left side, I'll get acceleration. So I'll just take the derivative of both sides with respect to time. On the left side, I get the acceleration vector. That's all I wanted. Let's move over a little bit. On the right side, I have the derivative of a product. So I'll do the product rule. So I'll do the derivative of the first. This is going to look strange at first. The derivative of the first times the second, plus the first times the derivative of the second. Now, first of all, what is going on here? Like, what is the rate of change of, that's not velocity, that's the rate of change of the speed. The rate of change of the speed is the thing I was describing before. It's the amount that your speedometer is changing by. that thing is going to be called a sub t. So we'll say let a sub t be how fast the speed is changing. Notice that it's not how fast the velocity is changing, it's how fast the speed is changing. In that case, we can write that a starts with a sub t times the unit tangent vector. Now we've still got some work to do over here. d capital T dt looks a little bit familiar. It has something to do with the unit normal vector. If we go back to the formula we used to find the unit normal vector, we had that n was t prime divided by its magnitude. So if I ever see t prime anywhere, I can rearrange this, that t prime is actually the magnitude of t prime times n. And that's what I'll do here. Here's t prime. So t prime is the magnitude of t prime times n. I've got the speed here too. What are these? Well, magnitude of v is the speed again. Magnitude of t prime, I'm not sure what's going on there, but that's how fast the unit tangent vector is moving. It's a scalar. So if I name this a sub n, then I get what I want. It's the speed times the magnitude of the derivative of the unit tangent vector. So our acceleration vector, it's in fact a combination of some acceleration like in the direction of motion and some acceleration that's perpendicular to the direction of motion. And we broke it up into these two pieces, and we actually got formulas for the two pieces. Anyway, the proof is finished. So let's put a box around, or do I get to put a box around them later? Yeah, okay. So I want to summarize what we discovered in this proof. The discovery basically is, yeah, this is good. If r is the position vector and the unit normal vector actually exists, like we have to take a lot of derivatives to get there. So if we can get to the unit normal vector, then it's possible to split up acceleration into speeding up and slowing down and turning. And we have formulas for these. At is just the rate of change of the speed. Okay. Is there a simpler way to write this? I guess we know for sure that if a vector I don't think this particular way of writing it is that useful formula-wise. So I think I'm going to leave it like this. But we're also going to note that you could find this acceleration by doing a projection. That if you dotted the acceleration vector with the unit tangent vector, you would get this number. And that's useful because if you know the velocity and the acceleration, like you can get a simpler form of this. So I think we're going to end up with two formulas for each, that AT is how fast the speed is changing, which is like a good way to think about it, but also we'll get a vector form of it that might be more useful in some situations. This is v over the magnitude of v. So we'll end up with v dot a over the magnitude of v. Here, v over magnitude of v, that's what t is. So this is another final formula for a sub t. Finally, we've got a sub n. We had a nice, well, a kind of nice form of it, which was this v. This is the speed times the magnitude of t prime, but that's not very useful at all. It'll be better to realize that it's the acceleration vector dotted with n. Now, what is this good for? Well, there's going to be like a simpler way to write this. I don't think I have time to prove it. Did we prove enough of the formulas? I think we proved enough of the formulas. I'll think about it. If I decide that we need another proof, I'll go do it later. It'll be a separate video. Yeah, but we can't. I can't spend too much more time proving these formulas. The reason that people like this kind of formula is it makes they look kind of symmetrical. That like we get v dot a over v for the tangential component, and we get v cross a over v for the normal component. The issue is that the data types of those objects are not even the same. Like if you dot two vectors, you get a number, and if you cross two vectors, you get a scalar. So you need to like take the magnitude in this one, but like, I don't know. I always worry about these formulas. These might be the ones that might come up for you in the future. I like all the other ones better, but yeah. Okay, let's get the last page here. So one last thing we were hoping to do was to figure out torsion. Torsion would be, so like here's something in the xy plane that has some curvature. Let's say that we drew a circle with radius 2, then its curvature would be a half. That's one kind of curvature. Another kind of curvature would be, what if you make a helix with radius 2? Now it's curved, but it's also like twisting out of its plane of like the plane that it's curved in. So this is another kind of twist, and that's called the torsion. So how do we get at the torsion? Well, we get at the torsion by defining one more vector, which is called the binormal vector. The unit binormal vector is, whoops, it's called B. It's defined to be t cross n. Now you might ask, what? Why? Like, what are you doing? Why did you do this? Well, we showed that the acceleration vector stays in the plane that's defined by the tangent vector and the normal vector. That t and n make a plane, and the acceleration vector stays in this plane. The thing is, there's vectors outside that plane. There's a whole space of vectors. And so we kind of want to know, like, well, if I have a plane, and I want to know, like, what's the other direction we could go? The binormal vector points in that other direction. If you want to get a vector that's perpendicular to t and n, well, there's a standard one, which is t cross n. This order matters. If you do the other order, you get the opposite vector, and people have just decided that this is the right order. So, what's good? What is this good for? What this is good for is that this binormal vector twists if there's any torsion. If there's any torsion, this binormal vector changes. If you just go around in a circle, like staying in a plane, in the xy plane, the binormal vector will it'll point straight up, and it'll stay pointing straight up. These B's. Now I'm worried that... Yeah, I pointed the right way. That like, we need some right-hand rule here, right? I've got like t, and then n points the direction that the curve is turning. And so t cross n ends up pointing up, and that's b. The point here is if you stay in a plane, your binormal vector keeps pointing the same way. So we can tell whether there's any torsion in the curve if the binormal vector is changing. So that's what we'll do. We'll say, hey, does the binormal vector change? Okay. So how do we get there? Let's take the derivative of the binormal vector. And as usual, we want to get the speed out of the question. So when we're just making up the definition, we do everything in terms of arc length. Okay, what is this? Well, it's the derivative of t cross n. And there's a product rule that says even if you have a dot product or a cross product, the product rule still works. It's going to be the first times the derivative of the second plus the derivative of the first times the second. dt ds. Which way does dt ds point? dt ds just was the beginning of the definition of n. So dt ds is a multiple of n. So this cross product, if you cross two vectors where one is a multiple of another, this cross product is 0. So the only part that survives is it's going to be t cross dn ds. Now this is not going to be our final formula. Like you've seen several times in this section now, we get s out of the formula so that we have something usable. But this is going to be what we start with. Okay, so how are we gonna proceed? First, what was the unit normal vector? Well, with s's in it, it was 1 over the curvature times dt ds. So n and dt ds are scalar multiples of each other. That's why this part went away, was 0. Because db ds is the cross product of t and dn ds, what does the cross product do? Well, t cross dn ds, whatever you cross, you always get something that's perpendicular to the two things you crossed. So db ds is orthogonal to t, and db ds is orthogonal to dn ds. That's just what happens when you take the cross product. If you have a vector valued function that has a constant magnitude, this was the trick we saw before with the unit tangent vector, then r and r prime will end up being orthogonal. In this case, I've got a unit binormal vector, so it has a constant magnitude. So the unit binormal vector also has to be perpendicular to db ds. A thing and its derivative should be perpendicular if the thing has a constant magnitude. Yes, that's right. Okay, so what did we end up with? Well, db ds is orthogonal to t, db ds is orthogonal to b. How can you be orthogonal to both t and b? If you're orthogonal to both t and b, then you have to end up being a multiple of n. So that means this db ds, it points in the direction of n, or maybe like opposite the direction of n, but it's parallel to n. So we can say that we know db ds is some multiple of n. Let's name that multiple. Remember, the point of all of this taking the derivative of the binormal vector was to find the torsion, so we'll name it t, but t is like taken, and capital T is also taken, so we'll go get the Greek tau, and that'll be torsion. It turns out it's a good idea to call this the opposite of torsion, and just try not to worry about that too much. But dBds was what we were planning to use to figure out if there was torsion. We proved that it's a multiple of n. That multiple is the multiple that we'll use. So what can we get here? Let's just, I want to divide by n, but the problem is that n is a vector, so that's not a very good idea. Instead, to get rid of a unit vector, you can make it go away kind of by dotting by itself. So I'll dot both sides with n. So I'll end up with dBds dot n is minus tau times n dot n. N dot n is the magnitude of n squared, so I get 1. So I finally have tau here. Tau is minus dBds dot n. This measures the torsion of a curve. Do I have a nice place to put that? Oh, I guess that's what goes in here. The torsion is minus dBds dot n. Okay, this section's really long. The theme here is like we tried to think about what curvature should mean. Curvature should mean how much does the tangent vector change. Then we wrote down that it should be dt ds, and then we came up with a good formula for it, and then we did an example. Now we've done that whole thing again. We were like, okay, well, what would torsion mean? Torsion would mean that this b vector is changing. So I'll write down dB ds, find out a bunch of stuff about it, and then finally figure out a usable formula. Then we'll do an example. So the last thing in this section is one more example. Do I have another page here? Good. Okay, so this gives us a helix, which is our prototypical object that has some torsion. Let's see if we can use the formulas to actually find its torsion. Okay, so I'm going to write down a plan because it's going to be kind of long. So the plan is I want to find b, but how do I find b? B is t cross n, so I'm going to have to go through all the stuff and find everything. So I need to find t, n, and then b. Once that's over, then I can find the torsion. I'll just use that formula at the end. It's minus dB ds dot n. Cool. As usual, when we have a something ds, we'll have to like get the s out of there, but we'll cross that bridge when we come to it. So this is kind of like a summary of the whole section. So see if you can follow this. First, we're going to find t. No problem. T is the velocity divided by the magnitude of the velocity, because it's a unit tangent vector. Well, the velocity is I take the derivative of the position. What's the magnitude of the velocity? The magnitude of the velocity is square root of a squared sine squared t plus a squared cosine squared t. That's a squared plus b squared. Combine all this together, and I get that the unit tangent vector is 1 over square root of a squared plus b squared times this vector v. So here's my unit tangent vector. I got a tangent vector, the velocity vector, divided by its magnitude. Now it's a unit tangent vector. That's t. Now let's go get n. Kind of want to change the color here. N, well, what's n? N is t prime divided by the magnitude of t prime. Well, I have t, so let's get t prime. Here's a scalar with no t's in it, so the scalar survives. Then I'll take the derivative. I don't see any nice simplification to do here, so I'm just going to leave it. Then we'll find the magnitude of t prime. The magnitude of a scalar multiple of a vector, well, you get to keep the scalar multiple. Then I'll square each of the components, add them together, and take the square root. That's a. Combine this together, and we'll get the principal unit normal vector. I need to multiply t prime by the inverse of this fraction. So the square root of a squared plus b squareds will cancel, and I'll get 1 over a minus a cosine t minus a sine t 0. Now at this point, I see some simplifying to do. I can cancel some a's, but I ask myself, is it worth it to simplify this? Am I going to have to do anything with this n? And the answer is yes, I need to go find b later, so it's worth it to simplify. So n is minus cosine t minus sine t 0. So I've got my unit tangent vector and my unit normal vector. Now I need to go get b. I don't know what's a good color for b. I kind of like this pink color. B, the definition of b is that it's t cross n. Okay, is there anything good to do here? Well, this scalar, again, we can pull out. And then I can cross the vector part of t and the vector part of n. Just do it with this determinant like we did long ago. I, j, k. Get the components of t. And the components of n. And then we need to do this determinant. Okay, what do we get? In the I component, what's at the 0? Oh, right, okay. In the I component, sorry. In the I component we get I times 0 plus b sine t. In the j component, I reverse minus b cosine t. So I'm going to have minus b, I guess I have triple minus b cosine t. So it's minus b cosine t. And then in the k component, I get a sine squared t plus a cosine squared t. That's a. So this is b. Yeah, it's a unit vector, so we're good. So I've got t, n, and b. Now I've done like the beginning of my plan. Now the torsion, I need to find dB ds and dot it with n. Oh dear. Okay, so dB ds. If you have an s and you don't want an s, you get out of it using the chain rule. What do you want? Well, I have a bunch of t's, so I'll do dB dt divided by ds dt. ds dt, what's that? ds dt is the speed, so that's the magnitude of the velocity. Which we found before. The magnitude of the velocity before was square root of a squared plus b squared. So all we'll have to do is find dB dt and divide it by square root of a squared plus b squared. Well, here's b up here, so let's find its derivative. First I have this nice scalar. Ooh, this looks good for us. Then I take the derivative. Okay. Do these cancel or combine? No, it looks like they combine. So I end up with 1 over a squared plus b squared. B sine t. Whoa. B cosine t. B sine t. 0. So this is dB ds. Now, is that what we wanted? No. We want the torsion, tau. To get the torsion tau, I need to do dB ds and dot it with n, and then take the opposite. So let's go. Where's n? Here's n. Let's get one more color. Green here. So finally, the torsion is minus dB ds, dotted with n. Let's take out the constant here. So I'm going to have 1 over a squared plus b squared. I've got a minus on the outside. I have b cosine t, b sine t, 0, dotted with n. Minus cosine t, minus sine t, 0. Okay, what else can we do? Let's factor out these b's. So I'll get minus b over a squared plus b squared. And then when I dot these, I get minus cosine squared t minus sine squared t plus 0. So this is all minus 1. So my final answer is b over a squared plus b squared. This problem's kind of huge, but it has a little bit of everything in the section. It has the definition of t, the formula that we use to find t, the formula we use to find n, the formula we use to find b, and then the formula we use to find the torsion. It doesn't have the curvature. We didn't find the curvature here, but yeah, there's a little of that earlier in the section. So in total, we finished everything that we wanted to do in this section. We got the unit tangent vector, the unit normal vector. We split up the acceleration vector into this a sub t and a sub n. That's the third objective up there. We computed those components, and then finally the point of that is that we can tell whether something is twisty or not if it has torsion. The torsion formula is right here in this example. Cool.